All right, so now we are at the position that we can actually look at the system responses to forced responses of the system that are particularly interesting. So one of the ones that we looked at so far was e to the st. Now, the next thing that's particularly interesting in a lot of systems, and I will give you a couple examples, particular examples, is when you have a sinusoidal drive. And I'm sure most of you can relate to this situation where you actually drive a system with a sinusoidal waveform, a sinusoidal current or voltage, and you want to see what it does in response to that, right? What's the output of the system in the presence of a sinusoid? And you are interested in the forced response because you're assuming that this sinusoid has been going on for a long period of time, so that you have the forced response, and then you basically are looking at the steady state response of the system. Now, if you have that picture, if you think about it that way, you really are looking at a system again, our favorite box with x of t and y of t. But this time, you're looking at it where x of t is some x0 cosine of omega 0 t plus some alpha. And we know if you're thinking about a steady state forced response of the system, and if this is an LTI system, it would only have a response that would be a cosine with some of a cosine form. So your y of t will be some y0, some different amplitude in principle, cosine of omega 0 t plus beta. Now you can see that actually, if you think about it, there are two things that are defining these waveforms by themselves, right? There is this magnitude and the phase. This magnitude and the phase of the response. And this is what we use to kind of define what we call a phasor. A phasor is really the amplitude and phase of this thing. So if you say, well, x0 with an angle alpha is my phasor, defines my input if I know my frequency is omega 0. And y0 with the angle beta defines the output. Right? That's all you need to define these things. So that's one way to think about it. Another way, which is more versatile, is to think about this as just the real part. So think about x of t being the real part of x0 e to the j omega 0 t, well, e to the j alpha e to the j omega 0 t. Because we know this is e to the j omega 0 t plus alpha, right? And you know that's cosine of omega 0 t plus alpha plus j sine of omega 0 t plus alpha. So the real part of that is this. And y of t is similarly y0 e to the j beta e to the j omega 0 t. So the part that's really defining this thing, describing it, is this and that. These two parts define and describe these functions. So essentially, you can think about these as the phasors. So these are the phasors. You can think about the input being described by x0 e to the j alpha, and the output being described by y0 e to the j beta, which is nothing but a polar representation of a complex number, right? So this is x0, and this is alpha. Right? So what is happening really, you can think about this as a vector with this magnitude and this initial phase that's rotating with the angular frequency of omega naught. And what you're looking at really is the projection of this thing on the real axis, which is the cosine, which is the real part, which is also the definition of cosine, right? So the only thing is that, so this produces this waveform. And similarly, for the y, for the output, it would be at a different phase and a different magnitude, but this produces the same thing. Again, it's a rotating vector. So what we really are doing, we are thinking about these vectors in the rotating frame of reference. So instead of thinking about these vectors constantly rotating, because we know that both the input and output vector are rotating, so one of them is, let's say this is the input and the output vector, right? So they're going to, you know, this has an initial phase of alpha, this one has an initial phase of beta, and they're rotating together. Since they're rotating at the fixed rate of omega together, their relative position remains the same. So it doesn't really matter. This part of it you can actually kind of take out and say, this stationary vector in that rotating frame describes my input, and this stationary vector in that rotating frame describes my output. Does this make conceptual sense so far? So why is it useful? Because now you can define transfer functions by saying, okay, I have h. Now this time, since your perturbation is only a function of the frequency, it's a cosine and sine. It's not a perturbation that's actually going it's not a complex perturbation. It's a very specific perturbation. It's really defined by omega. So in general, you can define it as h of omega, which you can define as y over x, the phasor y over phasor x, which is basically y naught angle beta divided by x naught angle alpha, which would be y naught over x naught angle beta minus alpha, which is the angle between these two vectors. An easier way to see this is if you write these as those complex quantities. If you write it as x naught e to the j, y naught e to the j beta and x naught e to the j alpha is y naught over x naught e to the j beta minus alpha, right? Which produces the same result. It's the phase difference. So the magnitude of this transfer function is this, and the phase of it is that. Of course, these are in general functions of omega. So in principle, you can write this h of omega. This h of omega now is also a complex number, as you can see, in general, right? Because it has a magnitude and it has a phase. Remember, the magnitude of e to the j beta, to e to the j anything is what? 1. So all of the magnitude part is captured here, and all the phase is captured in this. That's the strength of this notation, this complex numbers. That's why we use them. It allows you to treat the it basically decouples the magnitude and the phase. It's a polar representation, essentially, of a Cartesian set of numbers, a pair of numbers. So this essentially has a magnitude part and a phase part. Now, sometimes people, it would make sense to write it this way. But it would actually make even more sense and makes it consistent with everything else if you write it this way. So it's not only a function of omega, it's a function of j omega. When you say that, you're saying more actually about it, right? You're restricting it more. Now, why did I put that j omega there? First of all, you can see it's a function of j omega, because you have all the e to the j omegas here. But this makes it consistent, as you will see shortly, with the transfer functions that we've defined before. So this is essentially nothing but h of s, where s is j omega. In other words, evaluating the h of s, the transfer function of the system, on the j omega axis. Which makes sense because you're looking only at sinusoidal perturbations, right? And sinusoidal perturbations are represented by those things on the j omega axis. Because things that are off axis, in general, were exponentially decaying or exponentially growing sinusoids, or if they were on the real axis, they were exponentials, regular basic exponentials, growing or decaying, depending on which half plane they are in, right? Make sense? Okay, so that's basically it. And this phasor rotation allows you to define different things. So if you know this, for example, you can find your output y of j omega as a function of input x of j omega. So if you know what the associated phasor, in other words, phase and magnitude of the input is, then you can multiply it by the transfer function and produce the output, which is again a special case of what we had for h of s, x of s and y of s. But it's a useful thing because doing this allows you to calculate the transfer functions in a pretty straightforward fashion. So using this notation, for example, you can write impedances. as a for example. So you can write an impedance as V of j omega divided by I of j omega for a two-terminal device. So let's just pick it, and you can write this basically as the magnitude of the z of j omega and its phase. So let's determine this for a couple of different elements. So let's, for example, what is the impedance for an inductor in this form? Yeah, I mean, we already know that answer if you want to directly use what the result we already have. But we can also do it by applying a sine and cosine, right? For example, you can say if I of t is, let's say, I0 cosine of omega naught t, right? What is V? Let's do it directly first to see what it means. What's the relationship between the voltage and current of an inductor? We already have derived this, right? V of t is L di dt for a linear inductor. So I basically can calculate V of t as being what? I0, the derivative of this thing, which is omega, right? Sine of omega 0 t, omega 0, right? Negative. So, but I want to write both of them in terms of cosines because I want to find the relative phases. So how can I write this in terms of a cosine? What is the sine of t in terms of cosine of t? So you can write it basically, I want to write it in terms of something times cosine of omega 0 t plus some alpha. What is that alpha? Pi over 2, right? And you can see that, right? If you look at this, so if this is, let's say, this is cosine of alpha, this is sine, negative sine. So if this is the cosine, this is the sine of alpha plus p, pi over 2, right? So you can write this as I0 omega naught cosine of omega 0 t plus alpha. So what does that tell you? What does that tell you in terms of the response? And I forgot and the current voltage, there would be an L, right? There's an L, because there's an L up front. I dropped that L. So let's look at this. Cosine of, let's say, some number, alpha, a sine of something here. This is the sine, right? This is the negative sign. This is the negative cosine. So this length and that length, but it's in the other direction. So that minus sign cancels. So what you have here is that you see the magnitude of this thing is scaled by what? By L omega 0, the ratio of, so if you want to find the z of omega. So what you have is that z is L omega naught times the phase difference of these two. So cosine of pi over 2 over cosine. So what generates a phase of pi over 2 in complex domain? What is e to the j pi over 2? Think about it so this is 1, this is j vector, real and imaginary vector, right? So pi over 2, unity vector in this direction. What's this point? J. So this is j, right? So it is j L omega 0, or j omega L, which should not be that surprising because you remember what z of s was, right? What was it? Ls. So now if s becomes j omega, and that's why we show it as j omega, then you get that. So I'm not saying really anything new. It's just a different way of calculating things. In a way, it's actually a pretty boring concept because you already have done all of this. It's just a way of playing with the complex numbers and manipulating them. Similar thing you can do a similar thing for a capacitor, and then you will see that Z is going to be 1 over Cj omega naught. Z of omega, Z of j omega. For a capacitor. You can do a very similar thing, and it shouldn't be that surprising. Now, the good thing is that now once you're in this domain, you can do KVL, KCL, you can write everything, your impedances and admittances and everything in those terms. And then that allows you to calculate things directly. So, I don't know, let's just do an example of a phasor, just to give you a sense of how things are. So, if I tell you, okay, my voltage is, come on. So my voltage is, let's say, 4 plus 3j volts. So what is the phasor representation of this thing? If my input voltage is that, what is it in phasor domain? Well, you're taking something from a Cartesian set of coordinates, right? So this is 3 and this is 4, and you want to find what the phase and magnitude of this vector is. So what is the magnitude of this thing? 5. And what is its phase? Oh, yeah, it's tan inverse of 4 over 3. Which, I don't know, it's just, oh, I'm sorry. No, sorry, I had it the wrong way. This is incorrect, right? Because the real part is 4, and the imaginary part is 3. So it's this vector. And this becomes 3 over 4. So which basically becomes 5 with an angle of 36.9 degrees. Or if I tell you, so another example, so this was example. Another example, if I tell you what's the phasor representation of x of t being 2 sine of 2t plus 30 degrees, what would you do? What is the phasor representation of this thing? What's its magnitude? 2, we already know that. What's this phase? Don't say 30. You remember 30 is with reference to cosine. So you have to convert it to a cos, right? So what happens is that if this, think about this. This is sine of some function. I want to find a cosine associated with that. So what do I do? What's the best way to do this, to convert this to a cosine? Do you agree that if this is alpha, if I make this alpha, these two are equal? So do you agree that cosine of pi over 2 minus alpha is the sine of alpha? And likewise, the other way around. So I can play with that by saying that, well, this is really cosine of 90 degrees minus 2t minus 30 degrees, which is 2 cosine of 60 degrees minus 2t. So what is my phase and amplitude? Is it 60 degrees? Was my phase 60 degrees? No, because it has to be referenced with the right to the right omega. This is rotating in the opposite direction. So I have to flip this change. So I know cosine of alpha is equal to the cosine of negative alpha. So what do? I just flip the sign of the argument, which gives me what? 2 cosine of 2t minus 60 degrees. So that is 2 with an angle of negative 60 degrees. Right? These are pretty straightforward calculations. I just wanted to make sure that you're comfortable with them. Okay. Any questions on these? Now, the other thing you could do when you have something like this is to say, look, again, I can do the same thing with my impedances. Now I can basically have, if I have an impedance, z of j omega, I can really write it as a real part, r of j omega, plus an imaginary part, x of j omega. So this is a convention that's used very frequently. And or likewise, I can define, if I have an admittance, I can write it as a conductance g of j omega plus a b of j omega. So they really have 6 quantities here, 2 complex quantities, z and y, and 4 real quantities, r, x, g, and b. And they have 6 different names to make your life easier. So what are the names? We know this. What is the name of this guy? Z? Impedance. Right? And what is this? Admittance. What is this? Resistance. What is this? You know this? Conductance. You know what this is, right? Reactance. And who does know? Does anyone know what this is? This is called susceptance. So, susceptance, reactance. Okay, I missed it. So, I mean, okay. It's how susceptible it is to something, yes. Good question. No, there's a C in there, right? Yeah. Right, thank you. No, that's a susceptance. Susceptance. It's not a Dr. Seuss thing. Yeah. So it's basically how resistance, reactance, conductance, susceptance. Now, why is this important? Because it allows you to basically define an impedance. If you know it's driven by a sine and a cosine constantly, to deal with that way. Now, I said in the beginning that sine and cosine are important drives, but what kind of systems are the ones that actually use the sines and cosine drives? Can you think of some? Power systems, right? AC power, right? All the power network distribution, all those things, everything is in sines and cosines. So there's a lot of these calculations for power systems. You essentially just basically write the phasors and manipulate the phasors, just add them to KVL, KCL over phasors. So that's one thing. Can you think of another kind of system where these are very commonly seen? Radio frequency systems. All of the wireless communication system and all those things, because they use usually a carrier, a narrowband system. So it's a sine and a cosine that's being modulated for the information, but more or less the primary drive, for example, when you're making an amplifier, power amplifier for RF, or if you're making a low noise amplifier to receive something and all those things, those are mostly sinusoidal drives. So you deal with them like this. You deal with them in these terms. Now, one of the interesting things is that, for example, if I give you something like this, if I gave you an LC, right, at a given frequency, at one frequency, let's say at omega naught of 1 hertz, just for the sake of argument. And this is 1 ohm and this is 1 Henry. So what is the resistance here? Is 1 ohm. And what is the susceptance? So it's R. And what is X? Also 1 ohm. Both have units of ohms. Because this is, remember, reactance here is going to be J, or not, it's going to be omega L. Because the admittance of this thing is J omega L. So the J is taken out, so the X itself is omega L. So this times that, 1 hertz times 1 Henry gives you 1 ohm. So But the interesting thing is that at that frequency, there's another network that also gives you 1 and 1, right? So how can you convert? So if I have 1 plus j, and can you think of another network that, so what if I write it as something, how about this, 1 over 1 minus j? What is this? So this is, let's say I have something that looks like that. Does that work if I convert it to a regular form? So basically I get 1 plus j over 2. So 2 times that would have been 1 plus j. So it tells me that maybe I can write it as an admittance like that. But can I? Is it possible for me to write this like as an admittance? Like that. So this is going to be 1 ohm. And what is this going to be? If I make this, okay, so yeah, so I could make it an inductor or a capacitor, right? Do I have a choice? So if I make it an inductor, then what does it look like? Correct. The admittance would be 1 over Lj omega, right? And therefore, if I want to write it as so it becomes negative j over L omega. And I can choose the L so that this gives me that. So I can basically make this a 1 Henry. So it's an interesting thing. So it says, well, it really has to be 2 of that, right? 2 times that. So it's 2 and 2 because of that transfer. So this says they are equivalent. It sounds like it, right? Is that true? Are they equivalent? Only at that frequency. So it says that if you're operating at a very well-defined narrow frequency, you can replace this network with that network. Because they would produce both the same impedance at that one frequency. But their behavior versus frequency is different. But if you're operating at a single frequency, then you have a lot more leeway, because you can play all these games, because you're just trying to match 2 numbers to another 2 numbers, right? Okay, so that's for that. Now, when you're dealing with AC systems, there are a couple of calculations that are important, right? I mean, you want to calculate the average of an AC system or power and things of that sort. So we'll spend a little bit of time talking about that briefly. Again, there's nothing very profound about them, but I will just do it. So if you have a signal that's periodic with a period of t, how can you calculate its average? What's the average of this waveform? Show it like that. How do you calculate the average of a signal that's periodic with a period of t? Yes?
Integrate from 0 to t divided by the period of the cycle.
Yeah, integrate from 0 to t or negative t over 2 to t over 2, they're the same. 1 over t, and then v of t dt, right? So that's how you calculate or in general, if it's an x of t, let's say. Let's not even make it a voltage, just for now. We keep it general. Some x of t. You get that's the average. So what is the average of a cosine? Right. And what's the average of a sine? 0 as well, right? So these are obviously 0. What is the average of a cosine squared? 1/2, right? How do you come up with that? You know, cosine squared is 1 plus cosine of 2 omega 0 t over 2. This still averages out. You're left with the 1/2. And the same thing for cosine of omega. Yes. Sine of square of omega 0 t is 1/2. Right? Because in that case, for the case of a sine, this becomes negative. Still, that part of it doesn't matter anyway, because you averaged out, and that's gone. Now, one thing that's interesting is that if you have an element, so these are obvious things at this stage, but one thing that's kind of interesting about it is that if you have an element with a current I and a voltage V, And they're both sinusoidal. So let's say we are in this phasor domain. So you have I of t, that's cosine of omega 0 t plus times I0. And then you have a v of t, that's v0 times cosine of omega 0 t plus some phi. Because in general, they would not be in phase, as we've seen in several examples. What is the power delivered? So the power, instantaneous power, we know from the first lecture, is the product of these two, or maybe second lecture, I don't remember. Right? And that is basically I0 times V0 times cosine of omega 0 t and cosine of omega 0 t plus phi. But now if you're looking at an average power, what is it going to be? So it's average of that thing, which basically those come out of the integration. So you have an average of cosine of omega 0 t times cosine of omega 0 t plus phi. So what is this average, if you use that definition? So think about it. It's a product of two cosines, right? What is the product of two cosines? Can you write it as the sum and difference of two things? It's so cosine of alpha cosine of beta is 1/2 cosine of alpha minus beta plus beta plus 1/2 cosine of alpha minus beta, right? So if I use that, I get two terms. I get I0, V0. For the first one, both of them have 1/2. So I get average of the sum, which gives me cosine of 2 omega 0 t plus phi plus 1/2 I0, V0 cosine of theta. I'm sorry, phi. Right? The difference. So what is this average? What is it? 0. By that, right? Doesn't matter if you add a phase to it. It's just shifting it. So what is left is that the average power is going to be 1/2 of peak voltage and peak current product times cosine. And what's the average of cosine of phi? What's the average of a constant? The constant itself, right? So it's cosine of phi. This is called the power factor. Now, what is power factor? Why does power factor matter? Because you can have a large current and large voltage, but deliver no power. Let me give you an example. If you have an inductor, a pure inductor, if you drive it with a certain voltage or a certain current, right, what happens? You get a current and you get a voltage, but they're 90 degrees out of phase. How do we know it's 90 degrees out of phase? Because its impedance was J omega L. There was a J, right? So how much net power do you deliver? This thing, 0. It's all reactive, meaning that, yes, you put power in for half of the cycle, but you take it out in the other half of the cycle. So you don't put any net power in there, because it can't dissipate energy, right? An inductor. It can only store it. And in steady state, by definition of steady states, its net power cannot increase or decrease over time. So the net power has to be 0. It doesn't dissipate energy. So it's all reactive. How do we see that? Because if you remember that J in the impedance, right? The impedance of an inductor is J omega L. J means phi is what? What is e to the j? I'm saying, what is j? What is j as e to the something? What is e? Is e to the j pi over 2, right? What is this phase shift? 90 degrees, pi over 2. What's cosine of pi over 2? 0. So that's how it's captured here. Right? Make sense? So this is the power factor, sometimes shown as PF. And that's important. Actually, when you do power delivery in the power network, in the power transmission network and power generation, these fluorescent lights have actually look inductive because of the way they operate. So if you have a large number of these fluorescent lights, sometimes your power factor starts going one direction. The same thing is true about big electric motors. The big electric motors have big they appear inductive to the network. So they start creating a leading power. They call it leading if it's positive, and it's lagging if it's negative. They create a lead in the network. And that's not good for the network, because the network doesn't like that, because it means that it is constantly delivering power within a period and then taking it out. Delivering, taking it out. And when you start doing that, yes, you're not using net power there, but the distribution network is basically wasting power every time you're putting it in and taking it out, because it has some efficiency, right? So you're trying to adjust for that. So how would you adjust for that? Let's say you have a big electric motor and you're trying to make an adjustment so the power factor is proper, or becomes, or phi becomes small. How can you do that? Yeah. Use a capacitor, right? In parallel, because what it does, at that particular frequency, you can make the reactance of the capacitance to be equal. Well, in this case, it would be the susceptance of the capacitance, because it's in parallel. The susceptance of the capacitance to be equal in magnitude, but negative in sign, right, to that of the inductor, and it cancels it. So what's really happening is that when there's this power exchange within a cycle, right? You remember, said with half of it, for a little bit of it, it takes power, and then for the other half of it, or for the other part of it, it returns the power. What happens in this cycle? Yes, it does. The motor still does that, but it does it instead of with the network, it does it with a capacitor. So for the period of time that it needs the power, capacitor is the one that's providing it, and vice versa. And that's achieved by setting its susceptance to be exactly the same magnitude and opposite sign, opposite polarity of the network. Okay. Does that make sense? Okay. Any questions? Right. So this is a pretty straightforward, actually, part of this discussion. But now it leads us to something that's even more, I think it's interesting, which is, we are going to start the conversation today, and we are going to continue it next time, which is, what can you say about systems that are cascaded? So if you have a cascade of systems, let's say you have let's say for the sake of argument, you have 3 systems. So let's call this, and the first one has an impulse response h1 of t, h2 of t, and h3 of t. And they're associated h of s, right, the transfer functions. So you put some input x of t in, and then you get some y of t out. Or conversely, you could say you have an x of s or x of j omega as the input. But what is the relationship between y of t and x of t? How do you calculate y of t in terms of x of t? We already know this, right? How do you calculate this output in time domain? If you were to do it purely in time domain, our first approach, it's a convolution of h of t and x of t, right? And then from here to there, you get another convolution. And then you get another convolution. So basically, since convolution commutates, you can write as h of h1 convolve with h2, convolve with h3, convolve with x. So it's a convolution of the 3 of them. Now, how about in complex frequency domain, in the S domain? What is this output? Or P domain, the same thing. Right? Go ahead. H1 of S times x of S, or x of P. So it would be h1 of s, but then the next one would multiply by h2 of s and h3 of s. So in that case, you have h1 of s, h2 of s, and h3 of s times x of s. In other words, the aggregate, you can write based on these, you can write an aggregate impulse response, which is basically h1 convolved with h2 convolved with h3, because you can think of this as an aggregate impulse response. Or you can think of this as an aggregate transfer function. Okay? Does it make sense? Now, why is this useful? Why is this important? Because it allows you to deal with systems that can characterize independently. What do we mean by that? So what happens is that you can characterize systems independently, and the overall transfer function is just a product of them. And you will see soon that we can actually turn this into a sum. Right? How do you turn a product into a sum? It's a very famous invention or creation. It has a name. I'm sure you'll know it, just not thinking about it. How do you convert a product into a sum? Starts with an L. O. G. Logarithm. It's a logarithm, right? That's the whole point of a logarithm. The reason they created logarithm was what multiplication was not as easy as addition. So they said, okay, well, if you have these tables, each number corresponds to some, log tables, yeah. I mean, nobody uses them. Some people, at some point, some people were made to memorize them, but anyway. It's before our times, fortunately. So now, so that's the question. So how do we do that? Is there a way that we can actually use this concept to characterize systems in such a way that you can actually characterize them independently and then use that result? And that's called a Bode plot. So what do we mean by Bode plot? So let's start with a picture again. Something that you haven't seen before. Of course you have. So let's say you have something like this, a system but let's say this is in the lab. So you're sitting in the lab and you have an input. You want to kind of say, okay, you're given a black box that has an input terminal. What really it looks like, probably the black box has like two terminals. You can apply some sort of a signal source, and then you can take the output, probably hook it up to an oscilloscope, and look at the waveforms that come out. You have knobs and whatever. So the probe connects to the outputs, and I'm going to just skip all of that. So this is your system. So how do we go about characterizing this thing? So if I gave you a black box right now and say, well, go next door to the labs and characterize this, what would you do? What are the things that you can do about it? How would you go about characterizing it? So think about the situation. I'm giving you a black box. Say, go to the lab and characterize. Tell me as much as you can about this without opening it. Yes, Daniel.
Measure resistance and then maybe pump the current through it or see what voltage happens.
Yeah, but so that would be like for one port. But this is more of a two port. It has an input and an output, right? So how would you characterize that? What would you apply to it? Let's say, forget about let's say the input and output are both voltages. So you don't need to worry about that part, the impedance part for now. Yeah.
Maybe start by trying like just a DC input. First,
Okay, so start with a DC input, and then you will get probably a DC output. Let's say I tell you this is an LTI system, so you don't have to worry about nonlinearity. Yeah.
try to give as much impulse response as you can.
Impulse response. He says that give it an impulse response. So impulses are very nice theoretical tools, right? How do you generate that impulse in the lab? Without.
Really quickly.
Yeah. So sure. You made my point. You said short the battery or something like that. So yeah. How do you use an impulse without evaporating everything around you? A real impulse of energy would destroy things beyond your imagination. So you can make approximations of impulses, right? So you're not making a wrong statement. So you can hit it with an impulse, for example. Now, impulses, as we said, are very nice tools theoretically, but practically to generate them is hard because you can never generate a real impulse. And when you apply impulses to these systems, a lot of things can go wrong. I mean, they go into the nonlinear behavior, things can break inside. So you can have a surrogate for impulse even. You can have a step. But because if it's a linear system, impulse is the derivative of the step, so the impulse response is the derivative of the step response. So you could do that. But again, it's a derivative. Now, but it's also the problem with doing something like that is that, again, you can do it, and it's done frequently, but there's something even simpler than that. The problem with the impulses is that you're looking at transient events. Now, transient events have a lot of information in them if you can capture them well. The problem with that is that it's hard to capture. They're hard to generate. So can we think of something else that you can use to characterize a system? Yes?
Maybe like sweep through a range of frequencies.
Right.
Like
Sinusoid, sweep through a range of frequencies, right? So one of the other things you could do, you could actually apply a sinusoid, something very much more benign, right? Much less aggressive, but you can still get a lot of information from that. You don't need to really punch the system in the face at the end of the day. And that's true about humans too. You don't need to do that. You just need to interact with them, apply different range of frequencies, and look at individual responses on different things. Okay, look at them. Okay. Build the model in your head, and eventually you know them very well. You can predict what they do if you punch them in the face without having to punch them in the face. See? So the beauty of this thing is that you don't even have to do it if you know what you're doing. So you apply different range of frequencies. So what do you measure? So that's a good question. So you say, okay, you have different range of frequencies, and you start measuring something. So what is it that you're going to measure? Let's continue on that line.
So you probably want like relative phase to your input as well as like the amplitude of your the relative phase of your output to your input as well as the amplitude.
The relative phase of the output to the input as well as your amplitude. Or how about the relative amplitude of the output to the input? How do you do that relativeness, right? I mean, we already have done this similar calculations here, right? So we said that the transfer function, right? We said h of j omega was y0 over x0 e to the j beta minus alpha, where beta was the output phase, alpha was the input phase, and this is it. So we can plot this ratio. You can measure what the output, so you can measure what the output is, and then you can connect the other terminal of the oscilloscope to the input, so you have two waveforms. So let's say this is the input, you see a sine wave, and then you see an output that looks like this, to be the same frequency, so something like that, right? So you put a sine wave in, a sine wave comes out. So the only thing that's different between these two sine waves is their amplitude and their phases. There are two parameters you can measure. So you can measure the ratio of the output to the input as you change the frequency. So for each one of these frequencies, you make a measurement of this ratio, right? So you put a data point here, and then data point there, data point there, data point there, data point there, data point there. And then also you measure the relative phase, basically the phase of the output with respect to the phase of the input. And then you can put data points there. So you're measuring two different things. And then, of course, if you do enough measurements, you can get certain things here and certain plots here. So there's a plot. So what we are really plotting is, in this case so far, is h of j, magnitude of h of j omega, and the phase of h of j omega, because this was h of j omega, right? The only thing that this does, so now if I have a second system that I've characterized this way, and if I have a second, these are almost called Bode plots. Let's say I have two of these things for two systems, and they're in cascade. Can you tell me what this plot would look like for the aggregate, for the compound system, if I give you the individual ones? What would you do to calculate that one? The product of these, right? How about the phase part? It would be the sum of the phases, right? Because when you multiply these e to the j's, the phases just add. But it would be the product of them, right? Because if I have a h1 of j omega, that's magnitude of h1 and phase of h1, right? Let's say e to the j alpha. And the second one, h2 of j omega, that's the magnitude of h2 and the phase of h2. Then the product of these two, which is the aggregate response, becomes magnitude of h1 times magnitude of h2 and the phase of the two added. So that's good, but multiplying two plots is not easy, right? It's a lot better to add them. So how do you add them? Instead of plotting this magnitude, you plot log of it. Not exactly. Well, first of all, you do log base 10. And that becomes, that has a unit, that has a name. That has a name. Does anyone know what the name of that unit is? Go ahead. Not quite. Almost there. That's not decibel yet. It's a bell. It's a bell. And when you, bell is a big unit, so you plot the decibel. So you do this. I kid you not, this is serious. That's what it is. This is a decibel. Deci means 1/10, right? So that is a bell for the guy, Alexander Graham Bell, right? So bell is a big unit, kind of like thinking about microfarads. It's 1/1,000,000th of a farad, millihenries. So this is a decibel, but it has become so common that some people don't even know where it came from. Bell makes more sense. I mean, if you look at it, so okay, well, it's just log base 10 of the number is bell. And then since it's a big number, you want to get more resolution. So 10 times that would give you, so one bell is 10 decibels. So that's the decibel, dB. And you will see it a lot if you're an engineer, if you haven't already seen it enough. Right? So that's decibel. So once you express this in decibel, and you have, so now the beauty of this thing is that you can measure these in the lab with pretty benign systems that you don't have to really look at the transient response and look at it very quickly before it goes away, right? It's not something that you just, oh, if you blink, it's gone, right? It's the sine wave, it's there constantly, and then you put an input, and then you see the output, and you have time to measure it, and then you measure this phase difference and amplitude, and then you plot the 10 log of that, and that gives you, yes. Now, decibel is measured for power, right? So there's another subtlety to make it even more interesting in terms of what that decibel is. Now, if it's a ratio of powers, output power to input power, what is the power proportional to? Let's say if you have a voltage driven across a capacitor. So let's say the voltage across a capacitor is V of t, or V, some cosine of something, like V0 cosine of omega 0 t is coming across a resistor. What is the power delivered to this guy? Is Vz squared over 2R on average, right? It's proportional to V squared, or I squared, or product of I and V, right? Therefore, if you do this plot, now listen carefully to this. If you do this plot for ratio of voltages, since Bell was defined for ratio of powers, you have to look at the ratio of voltages squared. So output voltage squared divided by input voltage squared. But if you want to do it for the direct voltages, you could calculate that ratio and say, well, if it's squared inside the log, it's times 2 outside. So if you're doing it for voltages, you calculate 20 log base 10 of h of j omega, and you plot that. That's where that 20 comes from, if you're dealing with voltages and currents. Because at the end of the day, if you remember one thing, you can deduce the rest of it, which is Bell is the ratio of the output power to the input power. A decibel is 10 times that. If you're looking at voltages, you have to look at the output voltage squared divided by the input voltage squared, which gives you a factor of 2 outside the log, so it becomes 20 log of the ratio of the output. So if you're doing it really this way, what it means is that 20 log of V out over V in, or I out over I in. Make sense? Good? Anyway, any questions? Yes, Daniel.
What's an S parameter?
S parameters. Okay, so we haven't got, The S parameter is a ratio of so there are different ways to look at systems, right? Voltages and currents. The other way to look at it is that the ratio, looking at the incident power and the reflected power from the system. So the S parameters are the ratios of various reflected power to incident powers for different ports. So if you have one port system, it's the ratio of the reflected power to the incident power. If you have multiple ports, you can look at it for cross terms too. Any other questions? No? All right. So see you next time.